Welcome to the second part of electricity. In the previous video, we looked at the introduction to electricity. We also looked at static electricity. In this video, we're going to take a look at current electricity. So I had hoped that this part of the topic, current electricity, could be delivered in a single video, but the concepts are too many and they need some attention. So most of the concepts we're going to deal with them in this video. Then there is also a very important concept on how to analyze circuits that will be dealt in the video after this, so that we also solve as many questions as we can. Then after that, we take a look at practical electricity. So what is current? So when you use electrical appliances, electrical current flows in them. Okay, the flowing current means that the electrons flow in a circuit. A circuit is a complete path through which electricity flows. So a circuit is something that should have a start, and the same start should be the ending. It should be like a circle. It starts from here, it moves around and it goes back where it started from. That's what a circuit should be. So electric circuits start from somewhere, then they go back to where they started from. So in those circuits, electrons flow, and that flow of electrons is what we call as current. From now onwards, I'll be using an analogy for you to understand how the behavior of current, and the analogy is water in a pipe. So you should think of current as water that is moving in a pipe, or if you want, in a stream. So in short, current is defined as the rate of the flow of charge. The unit of current is ampere, represented by letter A, capital letter A, not small letter but capital letter A. Then charge, which is of course the flow of it, is what we call current, is the units are coulomb, represented by C. Okay, but current itself and charge are represented by I and Q respectively, meaning that capital letter I is used to represent current and capital letter Q is used to represent charge. The flow of charge is what we call current. So the connection between current and charge is this equation: Q is equal to IT. So the way I used to remember it, I just used to say quit. Yes, so charge is equal to current times time, where T is time in seconds. So this is the connection between charge, which is just an electron which is just the charged electron, and its flow, which is current. An instrument used to measure current is called an ammeter. So here are precautions which should be taken when using an ammeter. So for example, if you are doing a practical that has electricity, these are the precautions. First, an ammeter should be connected in series with a component to be measured. So if this is your circuit, batteries are usually represented by this, where these are the cells. So when you see this, where they are, one side is going to have a longer a line which is a bit longer than the line that is on this side. So a side that has a longer side is said to be the positive side, and the side that has a short one is said to be a negative side. So the way to connect an ammeter is, you need to get a wire on your circuit, then you connect it to one side of the ammeter. Make sure that this wire goes to the negative of the battery, and you get another wire connected to the positive of the ammeter. Make sure that this wire goes to the positive of the battery. Then you'll be able to measure the amount of current that flows through this circuit. Second, like I've said, the positive terminal, which usually is the red terminal, must be connected to the positive terminal of the battery, and the negative terminal must be connected to the negative terminal of the battery. So let's take a look at some examples where we are tested on how to use the relationship between charge and current. A bulb uses 20 amps of electricity in 10 seconds. Find the amount of charge that flows through it. So we have been given current and time, but we know that the formula is charge is equal to current times time. So we just insert current, which is 20, and time, which is 10. 20 times 10 is going to give us 200 coulombs. Example 2. 240 coulombs of charge were observed to flow through an integrated circuit in 2 minutes. What is the current flowing through it? So again, we've been given charge, which is 240 coulombs, and also time, 2 minutes, which if we convert to seconds, we're going to do 2 times 60 seconds, which is going to be 120 seconds. So that formula for charge equals current times time. If we solve for current, we're going to have charge over time. So charge is 240, time is 120. When we plug in, we're going to get 2 amps as the amount of current. So other than current, we look at another parameter which we measure in electricity. So this parameter appears in 3 different forms. They are kind of the same, but again they can differ, but mostly you're going to be using them like they are the same, but you should know the differences. So the first one is called electromotive force. So electromotive force, which is represented by EMF of a cell or battery, is defined as the energy supplied to each coulomb of charge within it. So the battery provides energy for the charge to be moving. So that energy which is given to each coulomb of charge is called electromotive force. So the units for EMF is volt, represented by capital V. Then there's another parameter called potential difference, which is defined, and also the short is PD, is defined as the energy converted per unit charge passing through a component. So in a circuit, in an electric circuit, you have components that you want to power. For example, you can have a circuit of a bulb. So a simple circuit of a bulb will have a battery and some wires connecting to the bulb. So as the current is passing through the wires, when they pass the bulb, some energy is going to be converted from electricity to, for example, if it's a bulb, light energy. So some energy is lost as current passes through that bulb. That energy that is lost is what we define as the potential energy, as the potential difference. Another way you can define this potential difference is just the difference in energy between 2 points. Okay, so potential difference is more concerned with points, this point and this point. What's the difference in energy? So in terms of electricity, we say what's the potential difference between this point and this point. Then electromotive force is about the energy that the battery supplies. Okay, but in essence they are all some kind of energy or voltage. So potential difference, the units are also volts. The next one is voltage. Voltage is just the energy needed to push a coulomb of charge between 2 points. So voltage is just the energy needed to push a coulomb of charge between 2 points, regardless of the location of the points. Electromotive force is concerned with how much energy the battery or the cell provides. Voltage is just the energy that is needed to push a coulomb of charge between any 2 points of your choice. Or potential difference is the difference in energy between 2 points, or the energy that is converted per unit charge passing through a component. It's a bit confusing, but I'm sure you're getting it. The units for voltage is also V, or volts. So electromotive force, potential difference, voltage, sometimes they differ to the same thing, but again they have their own specific meanings. But most when you're solving circuits, especially potential difference and voltage, you are going to look at it the same. Well, the electromotive force might be different, but it's essentially the same. And the formula that I used to get this is the same formula. So there is this picture I drew just to simplify the understanding. Let's say these are mountain climbers. So as they are climbing the mountain, they are eating some fruit that is of course giving them the energy to climb up the mountain or the hill. So if we want to define this situation in terms of electricity, assuming these people are charges, okay, so we can say that this one has at this point has some energy, let's call it energy 1, and this one has some energy NH2. All right, so the energy here might be higher than here since this one is tired. From here to here maybe start, so this one has a higher energy than this one. Okay, so these are the charges now which flow in a circuit. So the potential difference is the difference between the energy and the energy, meaning that if there is any component here, it means it's the one that has used up the energy that this one had. Okay, then the voltage is this apple that this charge is eating. Okay, so this apple is the one that's going to enable him to move from one point to the next. Then the EMF is the source of energy. So all this voltage comes from here. So what's the formula connecting current and what's the formula for getting potential energy? Potential difference, EMF and voltage. So the formula for getting potential difference, EMF and voltage is E over Q, where E is the energy and Q is the charge. Okay, so this is the formula for getting all of these parameters. So an instrument that is used to measure voltage is called the voltmeter. An instrument used to measure potential difference, EMF and voltage is called the voltmeter. So here are some precautions when using a voltmeter. The first one, which is different from the ammeter, is how you connect the voltmeter to the component that you are about to measure. So a voltmeter must be connected across a component in a circuit. What it means to be across is to be in parallel, as you are going to see. Then concerning the terminals, the same rule applies as in the ammeter. The positive terminal must be connected to the positive terminal of the battery, and the negative terminal must be connected to the negative terminal of the battery. So let's say you have got this circuit. You want to measure the voltage drop here or the potential difference here. What you do is you get your voltmeter. It has got two terminals, positive and negative. So you connect one wire from the positive of the battery here. So this is the positive side. You connect it to the positive, and also you get another wire from the negative side to the negative. As you can see, this is parallel to this. So this is how a voltmeter should be connected. An ammeter is connected in the same line as the component to be measured, or as the component to be measured. So we say an ammeter is connected in series while a voltmeter is connected in parallel. Finally, we look at resistance. The resistance in a circuit is the opposition to the flow of current. So as the current is flowing, resistance resists the flow of that current. The unit of resistor is ohm. So we use this symbol to represent ohm. The instrument used to measure resistance is called an ohmmeter. An ohmmeter. A device which provides some resistance in a circuit is called a resistor. Okay, anything that provides resistance to the flow of current is called a resistor. So normally resistors have a single value like 20 ohms, but there are some resistors which are designed in such a way that you can vary their resistance. Such resistors which can vary resistance is called rheostat or variable resistor. Finally, we take a look at Ohm's law. So the relationship which connects current, voltage, and resistance is given by what is called Ohm's law, represented by V is equal to IR. Voltage is equal to current times resistance. The relationship is called Ohm's law. Remember, voltage is being used to represent potential difference and the EMF. Okay, so this V is representing the others, but we don't use PD or EMF, we just write V. What we get, if the question, for example, is find the potential difference, we can use this, we get, then we can write at the end the potential difference is this. So this relationship is what they call Ohm's law. So to better understand or to visualize how Ohm's law connects voltage, current, and resistance is this. In a circuit, voltage tries to push a charge. The moving charge is the current here. Okay, so voltage tries to push current. So the movement of current depends on how much push voltage applies. Then resistance opposes this movement. So this is how these three guys are connected. So given this formula, V is equal to IR. If you want to find V, you can use just the way it is. If you want to find R, if you want to find R here, you divide both sides by I. So you're going to have R is equal to V over I. And if you want to find I, you can just divide both sides by R, and you're going to have I is equal to V over R. Let's take a look at an example. A current of 2 amp flows through a conductor. The conductor has the potential difference of 12 volts. Find the resistance of the conductor. Here is the solution. So the data that we have been given is of the current, which is 2 amps, resistance, which we are looking for, and voltage, which is 12 volts. So we're going to apply Ohm's law. So we can plug in the values. Actually looking for R, so we solve for R. So we solve for R, we're going to have V over I. We can plug in the values. When you plug in the V, which is 12, and the I, which is 2 amps, we're going to get 6 ohms. Finally, we look at symbols that are used in electrical circuits. When we draw a circuit, some symbols are used. The symbols commonly used are as below. So to show a connecting wire in a circuit, you have to draw a dot where the 2 or 3 or 4 wires are meeting. You have to draw this. If you just draw wires that are touching, we are showing this point, it might mean that the wires are not actually touching, but one is under the other. So you have to draw this to show that they are connecting. Also, if it's just a junction not crossing, it's the same thinking, a dot. Then wires which are crossing but not touching or not connected to each other, you can just draw this without a dot. A switch is represented by this small circle here, small circle. So this switch is open, meaning that there is no current flowing because they are not connected, this side and this side. So when you close this switch, that's when the current can flow. A cell or a battery is this. So this is one cell. If you do another one like this and this, there will be 2 cells. Then another one, a longer one and a shorter one, there will be 3 cells. This is positive, the shorter one is negative. So a battery is defined as a group of cells, and this is how to present it: a long one, a short one, a long one, a short one, or just a long one, short ones, and at the end of the day short one. But the better is a long one, a short one, a long one, a short one. A resistor is represented by this. Sometimes you can just draw a line, then you draw some zigzag, then another line. That's a resistor. Then a rheostat, which is a variable resistor. Draw a resistor, you put this arrow to show that this arrow it shows that this arrow can be moved to change the resistance. Like it can rotate, like the hand, the is it the hand of a clock which is moving to show the different times. So even this one, this shows that it can rotate to show different value of resistance. Light bulb is usually denoted just by a circle. Ammeter, it's A. Voltmeter, it's V. Then there is also what is called a galvanometer, which we might take a look at later, which is capital G. So for example, if you are doing a practical, you have been given this circuit and you want to write it on paper. The battery, you use this short, long, short, long, short. Then a bulb, just a circle. Inside you can even put this to show that it's a bulb. The ammeter is just A, so as you are going, you can put it here or here, it doesn't matter, depending on what you want to measure. So you just put capital A. A resistor, you just have to put this if it's not a variable resistor. A voltmeter, you just have to put V. So usually here, if you want, you can show, it's not important to show the polarity, to show that this is positive, this is negative. Just like this, it's okay. So this is how to break down something that is real to something that is on paper. So this marks the end of the first part of part 2. In the next part of part 2, we're going to have fun with circuits. Happy solving.